All right, and this is the sixth and last problem for my part. So we have a wheel that has a mass of 50 kilograms and a radius of gyration of 125 millimeters. If it rolls without slipping with an angular velocity of 5 radians per second before it strikes the step, determine its angular velocity after it rolls over the step. The wheel does not lose contact with the step when it strikes it. All right, so one thing to notice here is that, oh yeah, I mean, you're going in this direction, right? This is like your state one, this is your state two, going over the step. So you know you have a change in height. And because of that change in height, energy is gonna have to be involved at some point, right? So let's start by doing the free body diagrams, right? So for before, I have my wheel here, this. I know that my friction is gonna be this way, right? I have a normal force, and not Fj this way. And then my after, it's gonna be very similar, right? But it will be a little bit higher. Right, Fn, Fs, Fj, right? But it will be, the center of mass will be a little bit higher. And another thing to notice too is that since there's no slipping when it strikes it, we can assume that the normal force is always going to be acting radially inside this thing, right? So like, let's say I have the circle here, like during, let's call this impact. I have my circle. Like during impact, the force will always be towards the center of mass, right? That's the centroid of your shape or your center of mass. And yeah, so it will not. So basically, you will not have any torque on the system throughout this problem because of this property, because it does not slip. Because if it slipped, let's say, and then it got hit by the normal force in like this direction, let's say that was off center, then maybe you would have like some force vector this way, and then you would have some induced torque on your object. But since there's no slipping, since it's always in contact, we know that just by rolling, there's no torque acting on the system, basically. And you can use angular momentum to solve at least the first part of this problem, right? So that's the second part. We want to use angular momentum. So I'm just gonna do a small summary, right? So the angular momentum is equal to R times P, P being the momentum, right? And can rewrite this as R cross V, which is M R cross V, right? And basically the velocity is the velocity of the object, and R is the velocity, is the distance from a coordinate that we choose to put, right? So once again, we'll have to choose this coordinate smartly, or like well, to have like a good way of solving this, right? And yeah, so for my part, since it'll be easier for us to think about it this way, we're gonna put like the point, let's say here. Right, so like since the velocity is in this direction, it doesn't really matter if your point is here, here, or here, because only the y component is really going to affect the angular momentum in any way. Like it will only come up into that. We'll see when we do the cross product. So yeah, and so if I put it here, so I'll be taking my dimensions from this red spot here. All right, so the first thing I'll do then is find my angular momentum at state one, right? And also another thing is that when you do this angular momentum business, you have there's always two part of it. There's always the angular momentum that comes from the object itself rotating on itself, and you can now that's usually given by I omega, right, of the object. And you have the other one that comes from the object itself moving space, which is the one I describe here, basically. And so we need to find these two components of angular momentum in a way to solve this problem. All right, so I'm going to start by finding the one coming from the motion for the first one. So I'm going to do this. Right, so that's going to be basically just equal to this cross product here, R1 cross V1, right? And I know that my R1, basically, I'm going to give it a value of X, right? And you'll see why it doesn't really matter, but it'll be here. And then the height is 0.125 meters and 0, right? And where does this come from? Basically, it comes from just doing a R vector from this point here, up here, right? But as I said, like it could be something like this too, right? So that's why I call this X. But you always go up by 0.125 millimeters, meters, right? And there is no component in the Z direction, so this is why this is the value for my R. And then you do a cross product with V1, right, which is the speed of the object. Since we know that this object is going under rolling friction, we know, static friction during the rolling. We know that we can find its velocity just by multiplying the radius and omega. All right, so we know that it's going to be minus omega r, right? And 0, 0. Why negative? This is negative because it's going in the negative x direction, right? And omega r, this comes from the fact that it's rolling with static friction, basically. And yeah, and then we'll just like we'll just multiply it out, right? And then when we do the cross product, we get that it's going to be m. So the result's going to be a vector that's going to be 0. So let me do it the long way, right? So I j k x 0.1250 minus omega r 0, 0, right? But if I do this one here, I get 0, right? Then if I do this one here, I get 0. Then if I do this one here, I get 0, right? These two 0 plus 0.125 omega r, right? I know my omega is given to be 5 and my r is given to be 0.15 meters, right? So I get 0.125 times 5 times 0.125 equals, 1.5. And that value is going to give me 125 times 5 times 1.5, 0.09375, right? And see how this x doesn't really matter because it's not gonna provide anything basically to the angular momentum. And also note that we are equating basically the z component of our angular momentums because we're in 2D. So yeah, and then we plug this in, right? So we get the mass, which is 6. No, not 6. That was the last problem. So 50. Then we multiply by our result, 0.09375. And we get 4.68. All right, 68.75. All right. Now that we have this, we can do, let's say, the second part, which is the part where we take the angular momentum coming from the object rotating on itself, right? So I'm going to need I, which is just m times the radius of gyration squared, right? So that's 125 millimeters. So it's going to be 50, sorry, that's squared. So that's going to be 0.1, sorry, 125 squared, which gives a result of 0.78125, right? It's kilogram meter squared, if I remember well, for the units. All right. And therefore, the rotational part is going to be I omega, which is 5 times 0.78125, which gives an answer of 3.906. All right, so right now I'm doing this like as 2 separate steps, but usually you would just do this as like one line. Basically, these two would be mixed together because these two are basically these are going to be H1, the Z component of H1, right? And then similarly, I do this for the third one. All right, so I do it's the same equation, but this time I'm gonna have real unknowns. Right? Gonna be mass. My radius again, and not my radius, sorry, my distance vector is gonna be some value of x. My height now is gonna be 0.15, right? Because I'm on top of the step here. So by being on top, I now need my r to go like a little bit higher. So this is gonna be this distance here is actually going to be 0.125. Sorry, 1.5. Right? And my z is still 0. Then I do a cross product with my velocity, which is still again omega. I'm gonna call it omega 2 here. So we know it comes it's the one for the second one, right? And then times 0.15, which is the radius, 0, 0. And similarly as before, we get the result that it's gonna be m times 0.15 times 0.15 times omega 2. All right, when we put this 50 here, we get a value of 66.125 omega squared. I'm sorry, omega 2. Right, and then fourth part, once again, I already know that I is 0.78125, right? And so I just want to know what IW2 is, which is just going to be 0.78125. Right? And now that I have all of these little blocks, I'm able to fill up my main equation, right? Which is I want the angular momentum at the beginning. I'm just going to put Z because what we're doing right now is basically just comparing the Z axis, the Z component of the angular momentum. But you don't really need to do it because usually when you do 2D dynamics, this is what you would get, right? And so it would basically be 1 plus 2 equals 3 plus 4, right? If I go back to 1, it was 4.6875 plus 3.906. equals 66. So this does not seem right. Yeah, sorry, this should have been 1.125. All right, so this is 1.125 omega 2 plus 0.7815 omega 2. Then we isolate omega 2 on one side, so it's 4.6875 plus 3.906. Right, so I'm just I'm factorizing the omega 2 out. All right, and this gives as a final answer a value of 4.51 radian per second. All right. All right, and yeah, so basically this part here gives us the rotation right after the impact, let's say. Right, so as soon as you have the impact, right, so as you're here, as soon as you have the impact, you have a change of velocity, but you keep rolling and you go upwards, right? And that creates a change of energy, right? So we need to, because of that transfer of energy, the velocity itself will also change. All right. So we go back to our energy equation, right? So we have kinetic 1, UG1 can be equal to kinetic 2 plus UG2. All right, so let's say we place our reference for the zero height at the top here, right? Where at the center of mass of the wheel after the impact. Therefore, my no, actually, let's put it here at the beginning. It will be easier. Put it here, right? So you have no potential energy at the beginning, and then you gain some as you jump over the step. So this goes to 0. And yeah, and here, so for kinetic 1, of course, we need to consider the two types, right? We have the vectorial one, so like the one that goes in a straight line, and then we have the velocity, the kinetic energy coming from your object rotating on itself. So this becomes 1/250. V is just omega 2 r, right? R being 0. So yeah, I'll just write it like this real quick, and then I'll sub in the rest. Okay, so that's omega 2. And so I can just do 1/250. This is 4.51 times 0.15 squared plus 1/250, 0.7812 times 4.51 squared. Right, and this gives a result of 19.4 joules. Right, once you have plugged everything in. Then similarly, you want to do something for K2, right? But here we do not have the omega 3 that I'm going to call it now, right? So I have this, let's say, I'll keep 2 here. Just 1/2 I omega 3 squared, right? So we're going to sub in this one that V3 is going to be equal to R omega 3. So we have 1/2 mass R omega 3 squared plus 1/2 I omega 3 squared, right? Therefore, we get 1/2 m r squared omega 3 squared plus 1/2 I 3 squared. I'm going to pull out the omega 3 squared out of this, right? So I'm just left with known constants here. And when I plug this in, I have 1 over 2 times 50 times 15 squared plus 1 over 2 times 0.7812, right? Which ends up giving a value of 0.953. All right, and this is my key 2. And then I'm only missing the last one here, UG2. And since I said I'm going up the step, right? So I'm gaining 0.025 meters. That's my like delta H times mg, right? So it's going to be 0.025 times the mass 50 times A1, which gives 122.625 joules, right? And now put this all together using this formula here. And I have 19.4 equals wait a second, yeah, I forgot a 0 here. So this should be 12.262. All right. All right, then I plug this in, 0.953 omega 2 squared. Sorry, that's not 2, it's 3 now. Plus 12.2625. All right, then it means that I have 19.4 minus 12.2625 for 0.953, right? So I'm just bringing this one on this side and dividing like this. And then doing the square root. I'm going to do it now. And this gives an answer of 2.74 radiant per second, which is the final answer because that's what they're asking. They're talking, yeah, they asked about the angular velocity after it rolls over the step. And so, yeah, this is how you solve this problem.